Welcome back to ECE 320A. We're in video number 4 of Unit 2, and we're getting close then to completing Units 1 and Unit 2, and that means that you should be thinking about exam number 1, and there is some review material available in the D2L module titled Exam Number 1 Review Material. You might want to check that out. What we want to work through today is really just a formula or the concept of how do you find the complex power in a interconnected network or a network of loads. Is that easy to do? How much analysis is involved if we have S sub 1 all the way up through S sub 5 and they're interconnected in different ways, parallel, series, etc.? How can we find the total complex power of that interconnected network? Well, in fact, it's pretty clean, and I'll just make the conclusion right now, and we'll just work through that in a minute. But essentially, all you have to do is add these powers up. It doesn't matter how they're interconnected. You simply add all their real parts, you add up all their imaginary parts or reactive parts, and the sums of those, the algebraic sums of those, ends up producing the total complex power in that network. So let's write that out. And in fact, let me make very clear that how this collection of loads is interconnected, or the structure of that interconnection, the interconnection structure, whether those are series or parallel or some combination, which is what is illustrated here. There's no real defining interconnection structure. It doesn't matter. It's unimportant. That's one of the nice things about working with complex power. And to get us some notation established, let's just assume that subsystem, we'll call it lowercase l, or that each subsystem, which we're indexing with lowercase l, have the following power. The complex power of subsystem L we'll just denote as the real power, P sub L, plus the reactive power in an orthogonal direction. So now we have P sub L plus J Q sub L. That's the complex power of subsystem L. That's the notation that we will use. And we do have to make sure that we keep track of the sign, SIGN, of the reactive powers. If we now have a collection of interconnected loads, and let's just say that we have capital N such subsystems, or we have an N subsystem network, putting down on paper what I had said verbally before is the total power of that network is now just the algebraic sum from L equal 1 to N of the individual real powers, P sub L. So we now have P1, P sub 2, up to P uppercase N. We said we had N, capital N subsystems, and that's now in watts. That's the total real power of that interconnected network. The total reactive power is found the same way. We simply sum up from 1 to N the different reactive powers of each of the subsystems. So we now have Q1, Q sub 2, again keeping track algebraically of the signs, and that's now in vars. Q sub 1 plus Q sub 2 plus all the way up to Q sub capital N in vars. which now allows us to say that the total complex power of this interconnected system of loads is P subtotal plus J Q subtotal volt amperes. Or using the formulas again, that's just this sum from little l equal 1 up to n of P sub L plus J, and now in parentheses, let's say, because they all need to be scaled by this complex quantity J, the sum from L equal 1 to n of Q sub L. That's another way of expressing the complex power of this interconnected set of loads. One thing you need to make clear or understand or note is that if we now took the absolute value or the apparent power of the total system, that's not the same as adding up the apparent powers of each of the subsystems. We can't do that. We can add the component parts, but we can't add their apparent powers and expect to obtain the correct overall apparent power. And you can see that if you simply do a graphical depiction of what's going on. Suppose that we had just two loads. One maybe had a power of P1 real and a reactive power of Q1 for a total for a complex power of S1. And now if we moved from there or connected another load to that system that had a real power, let's say P2, and had a reactive power, and now let's say that it's not inductive, but it's actually capacitive in nature, Q sub 2, so that now the complex power of the second load is S sub 2, then the head-to-toe interconnection of those powers would end up giving us a total complex power S sub t, and hopefully you can see that the length of that total complex power would not be the same, since it's now really the third side of a triangle formed from S1 and S sub 2. We know that those particular S1's magnitude plus S2 magnitude is not going to equal the magnitude of that third side of that triangle. And that's a way to convince yourself that you can't add apparent powers to obtain the overall apparent power, but you can add the component parts of the real parts and the reactive parts, add those up, and those added up in total would give you the total complex power of the interconnected network. And it doesn't matter how those particular individual loads are interconnected.